Hello and welcome. We're going to take a look at another application of vectors, velocity. As we all know, velocity is a vector quantity because it possesses both magnitude and direction. We're taking a look at example 9, a canoeist who can paddle at a speed of 5 kilometers an hour in still water, wishes to cross a river 400 meters wide with a current of 2 kilometers an hour. Now, if he steers the canoe in a direction perpendicular to the current, we have to find the resultant velocity. And we also have to find the point on the opposite bank where the canoe touches. So a couple of things in here. First of all, we have to find the resultant velocity, which means the magnitude and the direction of velocity. And we also have to find the point where the canoe will land on the opposite side of the bank of the river bank. So let's get started by drawing the velocity diagram. So first, we're going to have the velocity of the boat, 5 kilometers an hour, represented by this vector. I'll call it VB. And next, we're going to place the velocity of the current, so tail to head, with the velocity of the boat or canoe. I'm going to call velocity of the current VC, that's 2 kilometers an hour. Again, it's up to you what symbols you want to use. It's important that whatever symbols you have used on the diagram or shown on the diagram must be used in the solution as well. Now, as you can see, the velocities are placed head to tail, and the resultant velocity or the real velocity of the canoe will be affected by both the velocity of the canoe and the river. So the resultant will be the vector that joins the tail of the first with the head of the second. So here we go. We're going to call this VR. Or you can simply call it R. Again, it doesn't really matter what symbols we use as long as we are consistent and use the same in our solution. So our job now is to find the magnitude of VR and the direction of VR. So I'm going to start off with the magnitude of VR. I know that VR is located in this triangle, and it plays the role of a hypotenuse, and we have the other two sides. So simple Pythagorean theorem is totally fine. So we'll write that VR squared equals VC squared plus VB squared. Oops. And substitute, we have 5 squared plus 2 squared, which equals 29, and makes the magnitude of the resultant velocity equal to square root of 29. Now we also need to know the direction of this vector, and for this we're going to use the angle made with the velocity of the boat or the canoe. So since we have all the sides, we can use any trig ratio we wish. Obviously this is 90 because we are going perpendicular to the current. But in our case, and in every case actually, I try to use the information given in the problem rather than using the information I've just found. Now, I'm going to call this the angle theta, and I will say that to find angle theta, I'm using the velocity of the current and the boat. Current is located opposite, boat or canoe adjacent, so tan ratio will do the job in here. So we'll say tan theta equals 2/5, which will make angle theta equal to inverse tan 2/5. Simply use the calculator to get the answer, and I used mine and I got 21.8 degrees. So with this, I've answered the question about the velocity resultant, which has the magnitude of root 29 kilometers an hour, don't forget, and it will head in the direction 21.8 degrees with the velocity of the canoe or VB. Next, we want to find out where would the boat land. So obviously the boat is heading this way, but it would land further down. So for this we have to draw the displacement velocity. So from one side of the river to the other we have 400 meters. So that would have been the horizontal displacement of 400 meters. Now the angle made between the displacement of the canoe with the width of the river would be the same as the angle made between the velocity vectors. So this would be the displacement caused by the current, and this will be the displacement resultant. So we're going to say that this angle will still be 21.8 degrees, and the resultant displacement, which is right here, is hypotenuse, and we're using the width of the river, which is 400, and the displacement down the river will be opposite. So since this is our unknown, we can use the width of the river of 400 meters in order to find the displacement down the river. So what this means that this suggests for the use of tan ratio. So we'll say that tan of 21.8 degrees would be equal to the displacement caused by the current divided by 400. So the displacement caused by the current will be equal to 400 tan 21.8 degrees, and we'll say that this will be 400 times the tan ratio of the angle, about 160 meters. So we're going to say that the canoe will land 160 meters far from the direction perpendicular to the current, so from here to here. Now let's take a look at the next question. Suppose the canoeist had wished to travel straight across the river. So let's draw the river one more time. And here we go. The river is still 400 meters wide. Okay. And we have to find the direction he must head and the time it will take to cross the river. So this time the canoeist is doing some calculations and trying to find out in what direction should he head so that he would land exactly. So the resultant vector will be across the river. So he's trying to minimize the distance traveled. So we're going to say that the velocity resultant now this time has to be perpendicular to the current. So this is velocity resultant. Now the velocity of the current, which is heading down, you can place it in any direction you wish, so, or in any position I should say we wish, so here or here, but I am going to place it down here. Okay, and the velocity of the boat will be this way around. So now we know that the velocity of the boat will have to make an angle or some angle with a horizontal or with a perpendicular to the current, so that with the current then this velocity will come down to become this. So the direction of the boat will go perpendicular or right across the other side of the river. So in order to find out the direction that he must head, then it means that we need to find this angle. So remember that to find this angle, which we are going to call this time angle alpha, I'm going to say that we have to use the given measurement. So what we do know is the velocity of the current, 2 kilometers an hour, which serves as the side opposite to angle alpha. And we also know the velocity of the canoe, which we have indicated by VB, and it's 5 kilometers an hour. So this is the measurement we need to find across our opposite angle alpha. This is the one that we can use. That's the hypotenuse, and opposite and hypotenuse suggests that we use a sine ratio. So we'll say that sine alpha equals 2 over 5, which makes alpha inverse sine 2 over 5. And second sine 2 over 5 would be equal to 23.6 degrees. Okay, so we're going to say that the canoeist must head at an angle 23.6 degrees from the horizontal. So with this we have answered the first part of the question. So the directions that he must head. Now the next part of the question is asking how long it will take, so the time it will take for him to cross the river. Now remember that he's crossing the river along this vector, so we have to draw the displacement vectors. Now remember, displacement vectors and velocity vectors will follow the same directions because they go in the same direction, right? And then we have here velocity vector, which in this case will be representing the resultant displacement. This would be the distance that the canoeist will travel. And this one here is how far down it will go. So the vertical displacement per se. Okay, I'm going to make this a little bit more interesting. It just say makes more sense. Okay. All right. Perfectionism is not always the best thing. Slows things down. Okay, here we go. So remember that we have to think, at this point, we have to think of two things, first of all. So first of all, we need to think of what we have to find, the time. And time is given as distance traveled divided by velocity or speed. Let's put it this way, divided by speed, where speed is practically the magnitude of velocity. Now, what is the distance that the canoeist will travel? So I want you to think, is the canoeist moving this way or is the canoeist moving this way? Now remember that the canoeist is heading in this direction, but with the velocity, the actual motion will be this way. So the actual displacement will go this way around. So if we want to know how much time it takes to go from this point of the river to this point of the river, which is a distance of 400 meters, because that would be the width of the river. So we're going to say that this would be a 400-meter distance. We need to know the speed, or in other words, we need to know the resultant velocity. So the speed is the magnitude of the resultant velocity. Now, according to our velocity diagram here, we have this triangle, right angle triangle, where we know all the velocities, so we can use very easily the Pythagorean theorem. We also know the angle. We can use SOHCAHTOA. I would go for the Pythagorean theorem because that allows me to use the exact values given. So in this case, I would say that the magnitude of the resultant velocity would be equal to 5 squared minus 2 squared. Remember that this plays the role of the hypotenuse. So hypotenuse squared minus the other side squared, which will give 25 minus 4, 21. So that will make the resultant velocity equal in magnitude to square root of 21. Now remember that this would be in kilometers an hour. So when we try to find the time using this velocity, we need to convert the distance traveled from one side of the river to the other, also in kilometers. So 400 meters would be equal to 400 times 10 to the power negative 3 kilometers divided by the speed of root 21 kilometers an hour. And that will give the time equal to, just simply use a calculator for it. So we have 400 times 10 to the power of negative 3, divide that by the square root of 21. So that was about 0.087 hours. And we want to convert this into minutes by simply multiplying by 60, because there is 60 minutes, or there are 60 minutes in 1 hour. So multiply that answer by the number of minutes in an hour. So multiply by 60, and you get 5.2 237, so 5.24 minutes. That's how long it would take to go from one side of the river to the other. So I hope this made sense, and stay tuned for the rest of the application questions. Thank you for listening. Bye for now.